Okay, part 12 of Applied Maths, Basic Linear Algebra. So we're going to start with 2D vectors, and vector as a word means carrier in Latin. So in maths that means it carries a point from one coordinate to another. So you may have heard of other vectors like disease vectors, it just means carrier. But in maths it carries something from one place to another, so it should only be thought of as a direction. But we can get a bit loose with that, especially in programming, so be aware. Vector v might be written like this, v with an arrow on top, or sometimes even that kind of half arrow shape. Technically a vector is not a point, but the distance between 2 points. But since you can move from the point 0, 0 to any point you like, a vector can describe that movement and it can effectively refer to a point by doing that. You can get the length of a vector. A vector is typically shown as a pair of x and y coordinates on a Cartesian plane. So you can think of a vector as being a triangle, with x and y being the two small sides, so you can use Pythagoras' theorem to work out the third side, which is the length or magnitude of the vector. Again, magnitude uses bars on either side of the thing. So if you get the magnitude of vector A, that's equal to the Pythagoras' theorem, and that looks like this, the square root of x squared plus y squared. So if your vector has an x and a y, square them both, add them together, do a square root, you get the magnitude of the vector. And the length cannot be negative. So a square root can give you two answers, positive or negative. That's just indicating that we always take the positive one, because a negative length doesn't make any sense. Here's an example. So if the x is 3 and the y is 1.5, so there's a point, the vector, beg your pardon, 3, 1.5. The magnitude of vector A is the square root of 3 squared, which is 9, plus 1.5 squared, which is 2.25, and that gives us roughly 3.354. So the length of that line is 3.354. To do it in code, you do square root of x squared plus y squared. That's C#, by the way. Square root is a quite slightly computationally expensive operation, which is why the fast inverse square root is sometimes used. You can add vectors together. So to add vectors, just add the x and y components. Simple as that. So two vectors made up of x1, y1, and x2, y2 gives you another vector, which is x1 plus y1, x2 plus y2. You just add the two x's, add the two y's. So for example, if you've got a position 3, 4 and a vector taking you there, if you've got a direction 8, 2, then you can take that position and add that direction on, and it'll take you to a new position. So 3, 4 plus 8, 2 gives you 11, 6, which, yeah, that adds up. So vector addition, very handy for moving things around on the screen or in a game world. Vector subtraction, on the other hand, it's kind of hard to find a very meaningful, at first glance, sort of image of this online. I've done my best though. As you might expect, so we subtract the two x and y values. So if you got vector A and vector B and you want to subtract them, it's x1 minus y1, x2 minus y2. So in this example, we've got a position 3, 4 and a vector that points at that, called P, vector P. And if we have a target at 10, 2 and a vector T that points at that, then T minus P is where you take T, 10, 2 and subtract P, 3, 4. So 10, 2 minus 3, 4, 10 minus 3, 7, 2 minus 4 is negative 2, 7, minus 2. Now if you use that as a vector from the origin, 7 minus 2, it takes us away down here, which doesn't make a lot of sense. But that green line, it would fit exactly on here. So that represents the distance from T to P. Okay, multiplication. Now there's a lot of ways to multiply vectors. The simplest one is scalar multiplication. You simply multiply x and y by some scalar value. Scalar just is the opposite of a vector. It's not made of multiple parts. So here's a constant multiplier, for example, k. If you take a vector x and y and multiply by k, then you just end up with kx and ky. That's all there is to it. So for example, if something has 5, 4 as its vector, and you scale it up by 3, you get 5, 4 times 3. 5 times 3 is 15, 4 times 3 is 12. Dead easy. Normalization, not quite so easy. Now, normalization is one of the bugbears I have about maths. It's a word that's used a lot, and it means different things depending on the context. But in this context, it means make a unit vector, or a vector 1 unit long. So to do this, take the x and the y of the vector and divide it by the length of the vector. And it's given that little hat symbol above it. So if the vector is normalized, v hat, then the way to get that is take the x and y values, divide by the magnitude of v. And we saw earlier the magnitude of v is x squared plus y squared all square root. So there's your final formula for a vector normalization. And here's an example. Take the vector 3, 1.5 and normalize it. So if you get the length of that vector and divide the 3 by it, divide the 1.5 by it, you get this here, 0.8944 and 0.945. I've just kind of shifted it upwards so you can actually see the difference. So a vector 1 unit long is called a unit vector. Unit vectors, unit circles, all very important to link things together. So for example, if you've got a vector 3, 4, then this is your classic 3, 4, 5 triangle, by the way. So 3 squared plus 4 squared gives you 25. Square root that, you get 5. So the length of that vector is 5 units. The normalized version of that vector, so I take 3, 4, divide it by the magnitude, which is 5, you get 0.6, 0.8. And here's some code that you might use in C# or maybe some other language. Excuse me. So the square root, that's Pythagoras theorem we saw earlier. The square root of x squared plus y squared. And then the new vector is the old vector divided by r for both components. As I said earlier, this inverse square root function is so common in computing that there's a function to approximate it. It's notoriously confusing. John Carmack, one of the most famous programmers out there, he didn't write even the function. It was basically blagged from Xerox Corporation, and he didn't fully understand it. So I'm not gonna look at it just now, but you can Google it. So one way to multiply a vector by another is the dot product. So instead of multiplying by a scalar, we're now multiplying by a vector. The weird thing is though, you still get a scalar as your answer. So there's two ways to calculate it. There's the geometric method. So a dot b is equal to magnitude of a times magnitude of b times the cosine of the angle between them, which is theta. Or you can do it the algebraic way. Take the two x values and multiply them, take the two y values and multiply them, and then add them together. This is almost always the way we will do it in computing because it's much less computationally expensive to do two multiplications and one addition than it is to do two multiplications and a cosine. Cosine is a transcendental function, so it'll take a lot of computing compared to just a couple of multiplications. So that's how you would do it in code. To get the dot product between two vectors, x1 times x2 plus y1 times y2. But what does that do? Well, it's kind of hard to get an idea of what dot product actually does. Here's a few examples that I've found people talking about it. They say, oh, it's the amount of vector A that goes in the same direction as vector B. Or take vector B and strengthen it or magnify it by using the part of A that goes the same way. Or apply directional growth of one vector to another, or project A onto B, then multiply by B. If that makes sense to you, then that's great, but I think it's really best to see it in action. So if two vectors are equal, the dot product, which is there, it gives us A dot B is A magnitude times B magnitude times cos theta. And because A is B, they're the same, they're equal, then B magnitude is the same as A magnitude. And cosine of theta, because theta is 0, will give us 1. So that just disappears. So A dot B is basically magnitude of A squared. But if two vectors are opposite, then dot product looks like this, same formula to start with. But if A is equal to minus B, well, this magnitude, it's this absolute value, that minus kind of disappears. But theta being 180 gives us minus 1, so that's where that minus sign comes from. So it's A dot B is minus magnitude of A squared if two vectors are opposite. That doesn't really mean much to me, I don't know about you, but if you turn it into unit vectors, this becomes more useful. So there we go, with the hat over A and B, telling you that they are unit vectors, they've been normalized. And if they are the same direction, then you end up with A magnitude squared, we just saw earlier, but A magnitude is 1, so that's 1 squared. So if they're exactly the same direction, then A hat dot B hat will always give you exactly 1 as an answer. So if you do the dot product and get 1, you know these are the same vector. If they're opposite vectors, then you'll get the negative of magnitude A squared. So you get negative 1. So if a dot product gives you minus 1, the two vectors are heading directly away from each other. In other words, if you make vectors into unit vectors, then do a dot product. You'll get 1 if they're exactly the same direction. You get something between 0 and 1 if they're sort of the same direction. You'll get exactly 0 if they are perpendicular. You'll get something between 0 and minus 1 if they're roughly in opposite directions, or you'll get exactly minus 1 if they're exactly opposite. Here's a few illustrations. Something less than 90 degrees, you'll get a positive dot product. Exactly 90 degrees, you'll get a 0 dot product. And more than 90 degrees between them, you'll get a negative dot product. What's that useful for then? Well, projecting, of course, things like shadows. You can do collision detection using separating axis theorem. You can determine whether things are going the right way. You can determine whether you're facing the same direction as someone attacking them from behind. You can find the angle between two vectors without using trigonometric functions. I don't find that terribly useful in games development, but I'm sure there's some applications for it. Or it can be used to reflect vectors such as light beams or velocity of bouncing objects. So projection of vectors. To project one vector onto another, first make the vector being projected onto into a unit vector. Then you do a dot product, so you get v, which is one of the vectors, times or dot product with the normalized second vector. And the result is a scalar. It's just a number telling you how far along line B the projection goes. So then you just multiply n hat by that. So here's the formula. The projection equals v dot product n hat multiplied by n hat. So v dot product n hat is a dot product. It will give you a scalar. So then you use that scalar to scale up the n hat, which is the vector. So you do end up with a vector eventually. If you didn't have that that factor in there, then you would have ended up with a scalar, which wouldn't be much use. Here's the code for it. Take two vectors, normalize one of the vectors, do a dot product between that normal and the other vector, and return the normal times that. So that n is that n. Sorry, wait. That n. Oh yeah, n's normalized. So that n there is that n hat, and that dot product is that dot product there. So that's how you would do that in code. And that's sort of a visualization. So if you've got a vector B along there, you've got a vector A here. We don't really need this line, but I'm put it in there for illustration. If you imagine that it's projecting it downwards, this line is perpendicular to B. So if you project A perpendicularly down onto B, there's A dot B hat. That's your projection. Not A dot B. Be careful of that, because that will scale up or down depending on the size of B. But if you make B a normalized vector, it's exactly 1 unit. It's going to be 1 unit in length, so you'll always guarantee a unit vector outcome. Oh, that's a lot to take in. Okay, so here's an example. So A is 3, 4, B is 10, 2. B hat, the normalized version of that, is approximately 0.98, 0.19, so scaled down so that it's 1 unit in length. So a dot b hat, take the two vectors, there's a dot product, with 3 times 0.98 plus 4 times 0.19, we end up with 3.7. That's the dot product. But then we take that 3.7 and multiply it by the original b hat, which is 0.98, 0.19. Multiply them up, you get 3.63, 0.7. So take these two vectors. If you project that vector onto that line, that's what you get. So it's went that far along the line. That's where the shadow will end of that object that has that size. So an object that size projected onto a surface going that direction, it will have a shadow covering that amount of the surface from the origin. You can also do reflection. You can reflect something in a mirror, that's a bit different. But we're talking about reflecting off of a surface, for example, light bouncing off something. To do this, you need to get the surface normal. There's that word again, meaning something different. We're not normalizing it. Well, actually, we'll be doing that as well, so don't get that confused. So usually the surface normal is perpendicular to the surface. Oops, sorry. So if here's your surface, x comma y, then the perpendicular line is minus y comma x. We swap them around, stick a minus sign in front, and that will always work. You can get a perpendicular line by always doing that. And the formula for the reflected line is the vector minus 2 times v dot product n hat times n hat. Now that hopefully looks familiar. That is the projection formula. So it's v minus 2 times the projected value. So yeah, here's a code that does something similar. Take the surface normal, so I assume we've done that bit already, and an incoming vector. Normalize the surface normal, that gives us n hat. Do a dot product between v and n hat, that's that part there, and then we return v minus 2 times that dot product times n. And that's how to reflect a vector. Now here's some really useful stuff. Geometric collision detection. You can check if a point's inside a circle. So here's our circle centered on 2, 2. It's got a radius of 1. And this object here is at 1, 1. You can visually see that it's outside the circle, but computers don't use eyes like that. They have to use numbers. So if you get the distance from 1, 1 to 2, 2, Pythagoras theorem, 1 squared plus 1 squared, 2, square root of 2, 1.41. So that thing is 1.41 units away from the center, and the radius is only 1. So if that edge there is 1, then 1.41 must be outside the radius. And that's why we do it. So subtract the point from the center, use Pythagoras to find the scalar distance. If that distance is less than the radius, it's inside the circle. Otherwise, it's outside the circle. To check if two circles overlap, we use Pythagoras to find the distance between the two centers. So it's much the same idea, but that point is the center of the second circle. And again, the distance in this case is 1.41. And the radius of the two circles, well, the radius of the larger circle is 1, and the radius of the smaller circle is 0.35. So add those two together, you get 1.35. It's less than the distance between the two centers, so the two things don't overlap. Now, let's just quickly go over that again. Use Pythagoras to find the distance between the two center points. If that distance is less than the combined radii of the two circles, R1 plus R2, then they do overlap. Otherwise, they don't. Now, rectangles can be axis aligned or an axis aligned bounding box if its edges are parallel to the x and the y. It's actually a lot harder to do if it's not, so let's stick with that for now. To check if a point is inside an axis aligned rectangle, look to see if the point's x coordinate is to the left of the rectangle's left border. So take the rectangle's left border, are we left of that? If we are, which we are in this case, then the point is outside the rectangle. And you do the same thing on all four sides. If the x is above the top, if it's below the bottom, if it's to the right of the right-hand boundary, then the point is outside the rectangle. Only if all four of these checks fail is the point known to be inside the rectangle. Now, this is just one approach. Obviously, you can combine that all into one. I think this is a more efficient method because you can return a false at any point and reduce processing. But I doubt it matters that much. And the last one of these ones is to do check if two axis aligned rectangles overlap. So The rectangle on the left and rectangle on the right, we can see by looking they don't overlap, but how would a computer do it? Well, check the right border of one of them against the left border of the other. And if it's to the left of it, that's what this case is here, the right border of this one is to the left of the left border of that one. No overlap. We could say, is the bottom of our box above the top of the other box? No overlap. Is the left of our, excuse me, is the left of our box to the right of the other box? No overlap. Is the top of our box below the bottom of the other box? No overlap. But only if all four of those fail do you end up with knowing for a fact that they overlap. And again, there are other ways to do it, but I think that's definitely the most understandable approach. I'm not going to demonstrate this one, but you can check if axis line rectangles and circles overlap by finding the closest point in terms of x and y coordinates that's inside the rectangle and closest to the circle. That's the hard part. And then once you've got that, you use Pythagoras to get the distance from that point to the circle, and if it's less than the radius, then they overlap. And finally, just a very brief overview of the separating axis theorem, which I mentioned. Not going into detail about it, but it's just one example of an advanced collision method. So with AABBs, we're limited to using boxes that are flat against the x and y axes. And if we rotate the box, it becomes an oriented bounding box, OBB. OBBs, you can't use that algorithm we showed earlier. Instead, you have to use the separating axis theorem. You can also use it on other convex shapes, not concave shapes though. So here's the quick rundown. It involves making your own arbitrary axes from each edge in one shape. So for example, if it's a square, you make four. In fact, in a square, you would actually only need two because the left and right edge are the same axis and the top and bottom edge are the same axis. So if you make two or more axes which are perpendicular to those edges, then you project both shapes onto that axis and you look at the projected sort of area, what they call the extents of those two projections. And if they overlap, you have not found a separation. So you check all of the axes looking for a separation, and if you find one, there's no overlap. And if you've checked all of the axes and don't find a separation, then they overlap. If that sounds complicated, it's because it is, or at least it is relative to what we've done so far. So that's why I'm not going to show you the details of that right now. Perhaps another time.